Okay, so we're off. So this is lesson 6. So the first thing we're going to do is just a reminder of how we determine magnitude and direction. And again, we sort of know that direction's a little iffy there. So I'm just going to ask you to take a minute, minute and a half to recall how we're able to find the magnitude and direction of a vector, an algebraic vector defined in 2D on a Cartesian plane. Okay, so I'll give you a minute to do that. All right, so let's take a look at this here. So if we kind of remember that in order to determine the magnitude, it was just a matter of applying Pythagoras, and it didn't matter which quadrant you were in. Okay, so whether A or B were negative didn't make a difference. You could always create a right angle triangle, and since you're squaring the side lengths, even if the component happens to be negative, you're squaring it, it'll give you what you need to find the length of the vector. When it came to finding a direction, so we had decided that we were going to use the angle from the positive x-axis, the easiest thing to use would be the inverse tangent of the using that triangle. Okay, where B sort of represents that height or the opposite, and A represents the adjacent. Okay, the issue was that, this gives you an angle between -90 and 90. So when you're in quadrants 1 and 3, in quadrant 1, no problem, it automatically gives you the angle from the positive x-axis. In quadrant 3, it gives you a positive angle between 0 and 90, but you need to add that to 180. Okay, and then when you're in quadrants 2 and 4, where the inverse tangent is going to be a negative angle, well, here, notice how I wrote it. It's 180 plus theta still, but theta is negative. So you're doing 180 minus that absolute value. Okay, similarly here, you get a negative angle when B over A produces a negative number. So it's going to be 360 plus that angle, which is actually going to end up being a subtraction because theta is negative there. So what we're seeing here is, I would say, the disadvantage of using this method of defining vectors, because when you want something that's often very important, say the magnitude, you have to do a little bit of work to get the magnitude. Not much, but still have to do some work. And then when it comes to determining a direction, well, it's actually quite annoying because it all depends on what quadrant your vector is in, okay? And you have to interpret based on your value of tan inverse of B over A. So what we have to hope, this is what we were talking about yesterday, that what we have to hope is that the advantages we get for working with vectors in this way are going to be worth our while. Okay, so what I want you to just quickly think about is what we had to do in the past to operate on vectors. Okay, now we know that things like, I want to go back to the sheet here, things like, finding the opposite of a vector, things like scalar multiplication, those were pretty easy when it came to dealing with vectors, say given the cardinal directions to define direction. Okay, but when it came to determining additions and subtractions, well, there was a fair bit of work, whether you did that by using sine law, cosine law, or whether you, split everything up into components, then add up the x components, add up the y components, and then turn it back into a single vector. Again, takes a certain amount of time. So the hope here is that this new way of considering vectors is going to save us some time, especially when it comes to addition subtraction, which is often what we're doing with vectors. Okay, so what I want you to do is I want you to take a bit of time here to think about if you have, and again, you might start with an example like a particular vector, 3, 4, but try to come up with a way of describing the opposite, a scalar multiplication, the sum or difference of vectors using a more general statement. Okay, and then lastly here, think about how you would determine a vector that starts at one point and ends at another point. Okay, so let's start that discussion again. So what we want to do here is we want to see how we could add vectors given this definition of the vectors themselves. Okay, so if I take a look at this vector u, so what did we say here? It's, if we think of this as the units going up by 1 and up by 1, we have the vector 5, 3. Okay, so if I want to add this vector v, okay, so what is this vector v? Well, this vector v is 3 and 1, 2, 3, 4. Okay, so let's do what we would have done in the past. Vector addition doesn't change. One would put those tip to tail, and you would determine the resultant vector. Okay, so resultant vector there would look something like this. And I guess if we used our original ways of doing this, well, the first thing you would do is determine this angle, okay, and then you can use that to help determine, this angle here, and again, use our formula to find the angle for vector v and find an angle inside the triangle. Okay, so this is how we would have done that. In fact, that complicates things, because at least in the past you were given these angles directly, and it was much easier to determine angles inside the triangle. But I'm going to guess that you noticed something that's not too shocking. But what did we notice here about adding these two vectors and what the resultant vector gives us? So who can tell me what great discovery we make here? There you go. You realize that if you look at the resultant vector, that can be thought of as just adding the two components in the x direction. So here 5 plus 3 to give us the x component of the resultant vector. Okay, and then here you can take the y component of the first vector 3 and add it to the y component of vector v to give you the y component of the resultant vector. So that means that by defining vectors using this method, things like addition, and we'll see similarly with subtraction, is just a matter of doing simple arithmetic. Okay, we take away the need to do any trigonometry. So as somebody mentioned the other day, this is very similar to working with vectors in terms of components, except now the components is how you're actually defining these vectors. You don't have to determine a component in the horizontal direction or in the vertical direction or whatever perpendicular system you're using. Okay, the vector is actually defined that way. So remember what we said. We said we lose the fact that the magnitude and direction are given explicitly. But if you can do all or most of your algebra without ever needing the magnitude and direction, then that's not a problem. Okay, so already we're seeing here that these operations of addition and subtraction, okay, and let's take a look at subtraction in a second, don't need you to know the the magnitudes and directions explicitly. So let's say I take the vector, v again, remember 3, 4, and I subtract vector u. So that's like adding the opposite of vector u. Oh, hey, wait a minute. How did I get this? That was one of the other things I asked you. Okay, is that if I have a vector u and I want a vector in the opposite direction, so in other words, that vector there, well, what does one have to do? If this is vector 5, 3, what does the opposite vector look like? Well, we realize it's just a matter of taking the opposite of each individual component. My x component goes from 5 to -5, and my y component goes from 3 to -3. Okay, so if we take this now and add it to vector v, okay, let's just confirm that we get what let's try that again, that we get what we expect to get. Okay, so let's see what our resultant vector looks like when we add those two together. Well, the resultant vector here is just -2 and 1. And let's take a look at the x component of my original vector, 1, 2, 3. Okay, and what's the x component of my second one? Well, -5. So 3 plus -5 gives you -2. So in other words, you're just subtracting the two components, 3 minus 5. Okay, and similarly for the y, 4, and then -3 gives you your 1. Okay, so we see that adding and subtracting vectors is all about just adding and subtracting the individual components. When you want to find the opposite of a vector, it's just about finding the opposite of the individual components. Okay, well, let's do the last one that was on our list. If I want to do scalar multiplication, if I want to take vector v and multiply it by 2, well, you can think of it as an addition, adding v to v. So in other words, if you're adding the individual components, you're just doing 2 times the x component and 2 times the y component. All right? Now, that's a pretty big get that we can add and subtract vectors so easily. All right. Now, you might sort of ask, well, okay, then why did we even bother defining vectors using that other method? Well, because in something like physics, you really are interested. Often the information is given to you in terms of a magnitude and direction. So you want to work with the information that's given. So when it comes to working in 2D, you'll rarely see an elementary physics course defining vectors in this way. But the reason why we're doing this more than how nice this works out is this is going to be our gateway to working with vectors in 3 dimensions. Okay, where having to deal with angles and working with trigonometry, as we saw, needing 2 different angles to define a particular point in space, gets much more complicated. Okay, so before we move on to the last part of this lesson should be a little shorter than yesterday's, I do want to introduce you to another way of describing these vectors. Okay, so are there any questions on what we've seen so far? Okay, so far what we've essentially seen is that if you want to add 2 vectors, actually here I've got it written out, okay, that if you want to take the opposite of a vector, it's just a matter of taking the opposite of each individual term. If you want to multiply a vector by a scalar, it's just about multiplying each component by that number. And if we want to add and subtract, it's just a matter of adding the individual components. And then subtraction, you can just think as adding the opposite. So subtracting 2 vectors is just about subtracting the individual components, because that's what adding the opposite is when it comes to real numbers. So essentially what we're doing is we're taking this new object of that contains both a magnitude and a direction, and we're turning it into a process of just adding and subtracting or operating on real numbers. And again, that's the best thing you can do in mathematics, is if you can take something new and relate it to a procedure that you already know how to work with. And we certainly know how to work with real numbers. Okay, but before we move on, there's actually an alternate way of describing these vectors. Okay, so far at this point here, we have described this vector using an ordered pair. Okay, so this vector here is the vector 5, 3. Okay, but there's another way in which we describe these vectors. And again, this is going to look a lot like what you would have done back in physics when you're working with components, is we define these very special vectors. Okay, now, what are the two things that are special about these vectors? Who can tell me why these vectors are likely special? Okay, so first of all, they're vectors of magnitude 1. Okay, good. What else is special about these vectors? There you go. They're both pointing in the direction of the positive axes. Okay, so these are what we call basis vectors. Now, I'm actually going to qualify that. This is what we call the standard basis vectors. So anytime I put an adjective to something, you should really be thinking, maybe there's other types of basis vectors. Okay, and well, I'll give you a hint there. Yes, there is. And we'll see that later on. But this is what we call the standard basis vectors. And what a set of basis vectors is, it's in this case here in 2 dimensions, a pair of vectors that we can use to define any other vector in R2, in this case here. So here, if I want to describe the vector 5, 3, well, I describe it as a sum of scalar multiples of these 2 vectors. Okay, and when we are adding objects together or adding scalar multiples of objects together, that's what we call a linear combination. Okay, so a linear combination means that the only thing that I can do with my objects is multiply them by scalars and then add and subtract them. Okay, so what would I have to multiply to I in order to produce the component in the x direction? Well, not surprisingly, it's just going to be 5i. Okay, and if I want to produce the y component, I just multiplied by 3. And what am I going to do with 5i and 3j in order to produce this vector 5, 3? What am I now going to do with these 2 vectors? You're just going to add them. And just to be sure that we see that, so again, you can think of it as addition. Hey, this is the diagonal of the parallelogram formed by these 2 vectors. Since the vectors are perpendicular, it's a rectangle. Or I can think of adding them tip to tail. So 5i plus 3j gives us the vector 5, 3. Okay, so this vector here can be written, okay, and it's completely equivalent, can be written as 5 times. Now, I'm not going to do this here because it's not quite so easy, so I'm just going to bold it. But what's the other way in which I might indicate this vector I or this vector j, given that they have, oh, that's right, not the arrow, we're going to use I hat, okay? I'm just going to bold it for now. It's a little tough to see that it's bolded, okay? So these are 2 equivalent ways of representing, excuse me, an algebraic vector in 2 dimensions, okay? Either explicitly as an ordered pair or as a sum, as a linear combination of these standard basis vectors. Okay, you'll see me using this version much more frequently because it's just easier to write. However, you will see the book use this version very often. Okay. So they are special cases of unit vectors. They just happen to be the unit vectors in the direction of the positive x-axis and the positive y-axis, okay? But let me just say this. Don't assume that all basis vectors have to be unit vectors. Sorry about that. It gets dry when you have to speak so much. Okay? So, we define vectors using these ordered pairs. We see that we can operate on these vectors, whether it's taking opposites, whether it's scalar multiplication, whether it's addition and subtraction. We can do that by purely working with the individual components. All right? That means that we don't ever have to know what the magnitude actually is or what the direction actually is to do these operations, okay? And that's a big win. But the big win is going to come when we get to 3D. And I'm hoping you can see how this is going to generalize very nicely in 3D. All right? The last thing we'll work at here is sorry about that, is a vector defined by 2 points. So let's say I have this point 3, 4, 8, 5, okay? And there's my vector. So can you tell me what the resultant vector is? Just by looking at it. Okay, so 5, 1. It makes sense because if I take this vector and I move it to the origin, 1, 2, 3, 4, 5, and 1, or I can even see it here, that in the x direction, I'm going to move 5 to the right, and in the y direction, I'm going to move 1 up, so 5, 1. But of course, somebody realized that, hey, wait a minute, it's just 8 minus 3 is 5, and 5 minus 4 is 1, okay? Problem is that these represent points, so we don't really subtract points, okay? I want to look at creating a vector, and what am I going to want to subtract to create this vector? I'm going to want to subtract vectors. So the way we're going to look at this is we're going to look at not the 0.34 and not the 0.85, but the vectors 3, 4, and 8, 5. And when I place these tail to tail here at the origin, what does this represent when I have a vector that goes from the tip of one to the tip of the other? What does that represent from what we saw earlier on? What operation does that represent? It represents a subtraction. And remember what that subtraction is. The subtraction is from the tip of the second to the tip of the first, okay? So that means, okay, that if I want to find the vector AB, that's going to be equal to, if this is going from the tip of the second, it means this is going to be the first vector, OB, whoops, OB, I guess I should be using an O, OB minus OA. Okay, and just to be, let's put vector notation around all of these just to make sure we understand that these are vectors. There we go. And so this is how we can determine. And of course, how do we subtract vectors? We subtract vectors by subtracting their components, okay? So anytime we want something that produces a vector, we want the operation to be on two vectors. So we just take the vector to that 0.34, the vector to that 0.85, which produces the vector that joins the two tips, which we recognize as an addition. So it'd be OB minus OA. In other words, from the tip of the second to the tip of the first. All right. So what we have now is we have a system for operating on the vectors defined in this way, all the operations that that we were able to do in the past. Okay. Now, those are not the only operations that we have on vectors, and we're going to see that by taking this perspective on vectors, we're going to be able to define other operations much more easily. Okay. But before we get into all of that, we want to make sure that we can upgrade all of this to 3D. All right. So what you're going to do now is we're going to start talking about how to define magnitude and direction for a 3D vector. Okay. Now, I would say magnitude should be relatively straightforward because I hope you recognize this as an exercise we've already done. All right. So we want to come up with a formula for the magnitude of this vector here. The question is, how are we going to define direction of a vector? Well, the hint I'll give you is that it will be at least it's going to be at least as annoying as determining direction in 2D. Okay, perhaps even a little more. So this is why we're going to be very motivated to perform all our operations without ever needing to do, without ever having to know the direction of this vector. Okay, so I'll give you some time to work on that, but there's just a question. Could you clarify once again why OB is considered the first vector and the second? Yeah, let's go back to our diagram here. So when we define direction, we saw that when we have a vector that joins the tips of two vectors that are placed tail to tail, okay, the rule was it goes from the tip of the second to the tip of the first. So since I'm starting at the tip of OA, that has to be the second vector. And since I'm ending at the tip of OB, that has to be the first vector. Okay, so if you go back and see how we defined subtraction with the vectors placed tail to tail, you would have seen that the rule we came up with was that the resultant vector went from the tip of the second to the tip of the first. So that's why this has to be the second vector, this has to be the first vector. All right, so hopefully that clears it up. So I'm going to give you some time now to come up with a formula and go through the process. Even if you have a conjecture as to how this works, please go through the process, draw yourself the diagram, okay? And then think about how we might use, or how we might come up with a way of defining angles, okay, presumably that would help us determine the direction of a vector in 3D. Okay, so we're back. So somebody made a comment there that, sort of describes what we're going to be doing. And essentially, this is exactly like the problem that we solved in one of the lessons, where they were asking us to determine the magnitude of a vector that joined opposite corners in, I think it was a cube, that one there, and there might have been a homework one that had a rectangular prism, but essentially we're going to do the exact same thing. Is we're going to split this up into two problems. Is first of all, we'll create the vector that connects the base, the opposite corners of the base. Okay. Now, what is this vector? Well, this is just the vector, 0, 0a plus 0b0. Okay. So here we see that this length is equal to a and this length is equal to b. So we know that this length is just square root of a squared plus b squared. And now we create a triangle with this side length and this height. And remember here, we're creating this sense of perspective, but this is kind of like the base of the box. This is the height of the box. So what we have here is a right angle triangle. We have to imagine that that's a right angle triangle because this height is perpendicular to the base of that box. So this is one side length. This side length here is just C. So if I want to find the magnitude of U, well, it's just the square root of the square of one side, okay, plus the square of the other side, and of course the square of a squared plus b squared, or the square of the square root of a squared plus b squared is just a squared plus b squared. And look what we have. A nice, easy formula. Okay, again, something we have to calculate. Let's keep in mind that that is the disadvantage of defining vectors in this way. But not only an easy formula, but one that just looks like an upgrade of the formula for 2D. Okay, so there we go. We have a, so nothing stops you from, so what do you mean by using components? Maybe I'm not sure what you mean by that. Because essentially A, B, and C represent the components of this vector. So can you elaborate on that question? Okay, so maybe, or like adding all the components together if it didn't start at the origin. Well, remember that this vector could be anywhere in space. It's still defined as containing the, three components. That's terribly drawn, okay? So in the end, regardless of where this vector is, it still would be defined by these components A, B, sorry, this is terrible writing here, okay? This vector would still be the vector A, B, C, okay? So let's say this was, we'll talk about it next time, how do we define a vector joining a point, say, 1, 2, 3, and the point 5, 6, 7. Well, I think you could probably imagine what you would do to determine the resultant vector from this point to that point, okay? And so this resultant vector is what you would be finding the magnitude of, okay? So I'm not sure if that helps, but if it doesn't, I think you'll see next time when we talk about vectors that are placed between 2 points. All right? So now, how do we define direction? Okay? Well, this is where, I'm going to tell you the answer, and you're going to really hope that we don't have to use these directions too often because there's a fair bit of calculating to do here. And what I want you to look here at this diagram. So here's my vector ABC. And I want you to see that 3 right angle triangles were drawn, okay? There's this right angle triangle to the component on the x-axis. So here, this right angle triangle, okay? This is a, this would be much easier to show in a classroom because I could show you a model much more easily, but you have to imagine that this is a right angle because this is one side of the box compared to this side length. This diagonal compared to this side length creates a right angle triangle. But when you look at this right angle triangle, you realize that if I consider this angle here from the vector to the x-axis, which we're going to call alpha, okay, you realize that here's my right angle, which means that the vector represents the hypotenuse of this triangle, okay? And this side length A represents the adjacent side to this triangle, okay? Let's look at another one here. Let's look at the triangle created by placing a line from the tip of the vector to the component on the z-axis. Again, it creates a right angle triangle. Here's my right angle, which means yet again, the vector is the hypotenuse. And what we're going to do now is consider the angle from the vector to the z-axis, which we're going to call gamma. And look what we have. Here's the hypotenuse. This side length C is going to be the adjacent side to that triangle. And similarly, this one's a little maybe tougher to see, although maybe that's just not too bad, the triangle that we create to the y component. Okay, so beta is going to be the angle from the vector to the y-axis. Okay, and so again, what do we have? Here's our right angle. So our hypotenuse side is still the vector, and this side length, which has length b, is the is the adjacent side. So the way we define the direction of this vector is using three angles. Okay, we use the angle from the vector to the x-axis, which we call alpha, the angle of the vector to the y-axis, which we call beta, and then the vector to the z-axis, which we call gamma. Okay, so three angles that we need to define the direction. Okay, one to each axis. All right, and let's see how we can calculate that. Well, again, if I take this here with the angle alpha, this side length A is just the adjacent side. So we can say that cosine of alpha is equal to, well, the adjacent A. Notice it's the x component of my vector over, well, what's the hypotenuse? Well, it's just the length of the vector, which of course means the magnitude of the vector. Okay, and I can do this with this second angle here, beta. Cos of beta is equal to, well, all I need is this side length here, which is just the length of the y component, b, and again, the hypotenuse is just the magnitude of the vector. And then finally, the angle to the z-axis, okay, again, the hypotenuse is still the magnitude of the vector, and this adjacent side is just length c. So cosine of gamma is c over magnitude of u. Okay, so not difficult equations, okay, just using right angle trigonometry, but it does mean needing three angles, and it does mean having to calculate these three angles. Easy to do, okay? Now, by the way, what happens if A is negative, say? Actually, it might be easier if we do this one here. I think I'm going to have an easier time drawing it no, let's make this one here. I think this is going to be the easiest one for me to draw. What if B was negative? What if my vector was somewhere in that direction? So the x component still positive, the z component still positive, but the y component definitely on the negative side. So we know the magnitude is always positive. What would that tell me here if the b was negative? What would happen when I calculated the angle beta? What happens? What does it mean when the cosine of an angle is negative? If you're not sure, take your calculator and check it out. What happens when you take the inverse cosine of a negative number? Come on, people. This is a big, important thing in advanced functions. What happens when you take the inverse cosine of a negative number? Just put in your calculator, do inverse cosine. Be more specific. Big, 79 seems like a big angle to me. There you go. Is you get you get an obtuse angle, which makes perfect sense that if the vector is on this side, that the angle to the y-axis is going to be greater than 90, okay? Actually, no, because you don't even need to do that, because cosine will automatically, it's not like sine or tangent that gives you a negative angle. Inverse cosine of a negative number does not give you a negative angle. It automatically gives you that angle greater than 90 degrees, okay? So again, put in your calculator, do cos inverse of negative 0.2 or something like that, and you're going to see it's going to give you an answer in the second quadrant, okay? Well, because then what that would mean is it's a little tougher to imagine on this 3D plane an angle from only the positive x-axis and then the angle going upwards. So that is an option to use two angles, sort of one angle from the positive x-axis. It's, I would say, much, much harder to imagine on a 3D plane, okay? Now, Enoch, the good news I have for you is that there's pretty much nothing that we're going to do in all the operations with 3D vectors that are actually ever going to need you to know what those angles are, okay? So that's how we define them, because it's a more natural way in 3D than taking an angle from, you know, the positive, from the positive x-axis and then measuring the angle to the z-axis, okay? But luckily, we won't ever actually need them. Okay, so I'm introducing them to you because you should know how one does define direction, but we're going to see that it won't be necessary when actually doing any of the calculations. All right, so alpha, beta, and gamma are called the direction angles, not surprisingly. And very often, instead of writing alpha equals cos inverse of A over magnitude of U, we just leave it in this form for our definition. So these are referred to as the direction cosines. All right. So let's take a look at the notes. Okay, just so that we can end this off. All right. So as we just saw, if we have a vector defined as an ordered triple in 3D, then the magnitude of that vector is just the square root of the sum of the squares of the individual components. All right. And if we want to describe the direction, like I said, luckily we won't need it very often. But if you do want to describe the direction, we describe it using these three angles to the three coordinate axes. Okay. Alpha, beta, and gamma. And luckily, in order to find the angle to the x-axis, you just need to use the x component. To the y-axis, just the y component. All right. So the next thing we saw, or one of the previous things we saw, was this idea of defining vectors using what we call these standard basis vectors. So the vector I, which is the vector in the x direction 1, 0, and the vector j, which is a unit vector in the y direction 0, 1. Okay, always assuming in the positive direction. Okay, any vector in the Cartesian plane can be written as what we call a linear combination of those two vectors. What does it mean to be a linear combination? It means we can multiply them by scalars and add them together. All right. Now we're going to see later on that maybe you don't always want to use two perpendicular unit vectors to define vectors on a plane. Okay, so that'll come up later on. This is why we refer to them as the standard basis vectors. Tomorrow, we'll see this tomorrow, or on Monday. I don't think it'll be too surprising that we're going to use something similar in 3D. All right. And if we look at these operations on 2D vectors defined algebraically, again, we see that adding the vectors is just a matter of adding the individual components. Subtracting is a matter of subtracting the individual components, and scalar multiplication is just multiplying each component by that scalar. And of course, the special one of that is the opposite vector, which is just multiplying each by -1. All right. So we're starting to get to the point where now we're operating on these vectors. The next thing to do is to upgrade everything to 3D. And then from there, we move on to the next phase, which is the idea of considering what it might mean to multiply two vectors. Okay, so any last minute questions before we go? And if people do want to stick around to see that question from the textbook, I don't mind taking that up. Okay, so any questions on what we've seen so far? Okay, so that'll be the end of the lesson. What was the question?
Wait, Tony?
Yeah.
Sorry. So just like in like the fourth question, the way we're supposed to like write the angles is with those cosines, right?
Yeah, or if you're being asked for the actual angles, you should be determining the angles. So taking inverse cosine of each of these, if what they're asking you. This is just how we tend to write the definition. But if they're asking you for the angles themselves, you should be calculating alpha, beta, and gamma. Okay?
Okay.
And again, you should already know a priori that if these numbers are positive, any component that's positive is going to generate an angle between 0 and 90, and any angle that's negative is going to produce an obtuse angle. Okay. So again, the example: if my vector was going in this direction, let's say my vector was 2, -3, 5. I know that my angle to the x-axis should be acute, the angle to the z-axis will be acute, but the angle from the y-axis should be obtuse. Okay, so that's sort of, if you kind of don't get that, it means you probably inputted something incorrectly into your calculator.
Right, okay.
Okay, great.
Great, thanks.
Okay, anything else on this stuff?